Slash, do you mind doing it again? Okay.
Yeah, I think it already started recording for me.
Okay, cool. All right, so folks, I'm going to go ahead and share my screen. We're going to take a look at sections 5.6 and 5.7. If you go in Canvas, the blank notes should be there. So if you have a printer, you're always welcome to print out the notes before class and then just write right on it. Or if you want to upload them to your tablet or however you want to do it is totally fine. But at the end of this session, I will upload the complete notes from today. And then when we get the video processed, the video link will also be put into Canvas, okay? All right, so let's begin. I feel like with that notability slide that always comes up when I click on it, I feel like I should be getting paid to, like, you know, do stuff with their app. But anyway, we're going to start here with 5.6. Okay. All right. So 5.6 and 5.7 are a couple new formulas. All right. So for 5.6, we're going to be looking at integrals involving exponential functions. And then we're also going to take a look at integrals involving log functions. Now, we've kind of already seen them. I've tried to work them into some of the questions that we've already seen. So this shouldn't necessarily be new content, but it's a good chance to practice some more rules, especially after we learned the U substitution last time. All right, so I'll give you a moment to copy these down, but we're going to start with integrals of exponential functions. And so with integrals of exponential functions, there's two main cases that you see here. The most common one that you're going to see is when you have an exponential function with a base of e. So this e to the x is probably the most common. The nice thing about that is the integral of e to the x is e to the x plus c. Now, when we have a different base, okay, so every once in a while we deal with a different base. Now, that's not as common, but it's kind of nice to know that we could at least still follow the same rule. So the rule for when the base is not e is you just have the same thing. So you have a to the x, it's going to be a to the x, but you're going to need this additional part where you divide by natural log a to compensate for the fact that it's not a base e. All right, so those are the two rules that we're going to use for the exponential functions integrals, okay? Now I'm going to scoot over to the side and we can take a look at these integrals of log functions here, all right? So the most common one, and we've already seen this one, is our one exception to the power rule. And that is when I have x to the -1, then my integral is not going to use the power rule, but it's going to be natural log of x plus c. I would suggest that you write not just that it's the integral of x to the -1, but that it could look like this, 1 over x dx, or that it could look like dx over x. All right, so just to be aware that it could look like some of these other forms and that it's important to be able to recognize those because we can't use the power rule for this particular situation. Now, there's two other rules, but I'm going to say these are more like bonus rules. I want you to see them. I want you to know that they exist, but most likely, if you are ever expected to use them in the future, you'll just be able to look them up on a table of integrals, okay? So the last two are not ones that you need to memorize, all right? So these two do not need to memorize, all right? But let's just see how this works. So if you have the integral of the natural log of x, then what happens is you get x natural log x minus x, okay? And if you happen to have a natural log, but it does not have a base e, like a log base a, then the formula, similar to the exponential one, is almost the same. You just have to divide by that natural log of a. All right, so those are our formulas. All right, we're going to focus mostly on the following ones today. We're going to focus mostly on this one, and on this one, okay? And I would say even this second one is a little bit less common. All right, so here we go. We're going to walk through a bunch of examples, see how it goes. Feel free to interrupt me and ask some clarifying questions, okay? But we're going to start here with example number 1. So example number 1 says the integral of e to the x dx. So this one is pretty straightforward. All we need to do is say, I know that the integral of e to the x is e to the x plus c. And that's it. Okay, that's literally all you need to do for example number 1. But what I wanted to do was to put it in contrast with number 2, okay? Because the thing that I'm interested in is what's in the power. So there's an x in a power over here, but over here, the power is negative x, okay? Now I know those two look super, super similar, but for example 1, you do not need u sub. All right, it's as straightforward as you can get. It's literally a rule right off of the out of the rule book. But for example 2, guess what you need? You need to use u sub, okay? Because e to the negative x is not e to the x. It's close, but it's not e to the x. So I'm going to go ahead and set up my u sub here. My u is going to equal negative x. It's the thing in the power. And that was a pattern that a lot of us caught on to last time. That means my du is going to equal negative 1 dx. And I noticed that in my equation, I have just a dx. I don't have that negative 1. So I'm going to divide this negative 1 to the other side, and I'll get negative du equals dx. So what that means is everywhere I see a dx, I can replace it with a negative du, okay? And everywhere that I see a negative x, I'm going to replace it with a u. So let's do that u sub. We've got the integral of e to the u times negative du. So that negative means it's really times a negative 1, and I'm going to bring that negative 1 out to the front. So I've got the negative integral of e to the u du. Now this looks a lot like question 1, so it's negative. The integral of e to the u is just e to the u plus c. And the last thing I need to do is put my x back in, so negative e to the negative x plus c. All right. Any questions so far on 1 and 2? All right. Let's move on to example 3 and 4 though. So we're going to get a little bit more complicated, but we're still going to be looking for some variation of using e to the x and that integral, and usually with some u sub. So let's take a look at example number 3. Any guesses for what we would put for our u here?
-2x cubed.
Perfect. That negative 2x cubed. All right, that's going to make our du equal to negative 6x squared dx. And when I look at my equation, I have an x squared dx, so that'll take care of this part. That means I need to divide that negative 6 to the other side. So negative 1/6 du equals x squared dx. And then everywhere that I see the negative 2x cubed, all right, so up in this exponent, I can put a u. Now, I'm going to go ahead and substitute. So I'm going to get the integral of e to the u times negative 1/6 du. And when I go ahead and pull out the constant, I take out the whole 1/6, that negative 1/6, then I get negative 1/6, the integral of e to the u du. And the integral of e to the u du is just e to the u. So negative 1/6 e to the u plus c. And our last step is to go ahead and put back in our x's. So negative 1/6 e to the negative 2x cubed plus c. All right. Okay. So let's take a look at question number 4. All right. What do we think our u should be for question number 4?
Would it be 3e to the x minus 2?
Yes, it would be. And I know that's a little bit bigger of a u than we've been seeing, but that's okay. So 3e to the x minus 2. All right. Now, if we have that as our u, that makes our du equal to 3e to the x dx. What happened to that minus 2?
It's a constant, so that they cancel.
Exactly. 2 is a constant, so when you take the derivative, it's going to go away. So now let's see if we need to do any work to the du. I've got e to the x dx, which matches with e to the x dx. So that means I'm going to need to divide that 3 away in order to substitute. Okay? So let's go ahead and plug everything in. So I've got the integral of u squared times 1/3 du. Now I'm going to go ahead and take that 1/3 out to the front. Okay. Now what rule am I going to use to find my antiderivative here, or my integral?
Power rule.
Yeah, it's going to be power rule. Okay, so here we want to make sure we use our power rule. And when we do that, we have that 1/3 from the outside. And then u to the 2 plus 1 is 3, and the reciprocal of 3 is 1/3. And then plus c. Okay. Now I'm going to take the 1/3 times the 1/3 to give me 1/9. And u cubed plus c. And my last step will just be to put my x's back in. So 1/9, 3e to the x minus 2 cubed plus c. All right. All right. So let's go ahead and move on to the next two examples, example 5 and example 6, okay? And so I'm gonna leave this up on the screen, give you guys a few minutes to try them out, all right? So you're gonna try and figure out what's your u, what's your du, and then what rules are you gonna need to find the integrals, all right? So I'll give you a few moments to work on that, and then we'll check over those. And then we'll move into some definite integrals just to practice with the bounds. All right, so let's take a look at example 5. So I have my work up here. Let me just talk through it quickly. So I said that my u was going to be the thing underneath the square root, so the 1 plus e to the x. And then I found my du, and just like in example 4, the constant went away, so the 1 went away, but then I still had e to the x dx. And that actually matched up perfectly with the e to the x and the dx in the equation, so I didn't have to move anything else. And then when I substituted everything in, I got the integral of the square root of u du, which I knew that I should write as this power of 1/2 here. And once I wrote it as the power of 1/2, I could see that I needed to use the power rule. So I did 1/2 plus 1. That got me a new power of 3/2. And then I knew the power, or the coefficient in the front, needed to be the reciprocal. So the reciprocal of 3/2 is 2/3. And then my last step was to plug in my 1 plus e to the x back in. All right, so that's what I got for my final answer. Does anyone have any questions on number 5? Okay. Question number 6. I feel like you guys have been super good at identifying the u's. So I think we got u equals x to the 4th. And then my du would equal 4x to the 3rd dx. Now, when I look at what I have in my equation, I have a 2x cubed dx. So what should I do to this line right here to make it match what I have in the equation?
Divide by 2 on both sides.
Yeah, divide by 2, good. So 1/2 du equals 2x cubed dx. Now, everywhere I see the orange in the equation, I can replace it with 1/2 du. So here we go. The integral of e to the u times 1/2 du. Now, if you're getting like, not bored, but you're like, oh, I don't want to write the 1/2 here. I know it's going to come out to the front. You can go immediately to this step. You can say 1/2 the integral of e to the u du. All right, so you don't have to write that at the end of every one if you feel ready to kind of pull it out to the front right away. So I get 1/2. Well, this is actually pretty easy because e to the u is just going to be e to the u plus c. And my last step is everywhere I see the u, I'm going to put my x to the 4. And that is number 6. All right. So it seems like we're doing pretty well here. Either that or folks who are doing really well are answering all the questions, and folks who are feeling a little lost are just sitting there feeling lost. So this is the tough thing for me, right? I can't see you. I can't necessarily like, you know, have open practice time and look at your face and know that you need some help. So if you need some help, it's okay to ask questions, or you can stick around at the end and ask me some questions then, okay? All right, well, in the meantime, let's go ahead and move on to example 7, okay? So let's do example 7 together, and then we'll do some of those other ones as practice, all right? So the difference between this one and all the other ones is now I have bounds. So I have my, I have my bottom bound of 1, and I have a top bound of 2. And so if I need u substitution, I'm gonna have to substitute those as well, all right? So let's look at this problem. I notice that I have a 1 minus x in the exponent, and that's not just an x, so that is a clue to me that I need to use u substitution. So u equals 1 minus x. That makes du equal to -1 dx. And I don't see that negative there, so I'm going to divide it to the other side for my substitution. And then I'm going to go ahead and find my lower number if it were a u. So u would equal 1 minus 1, which means my bottom bound will be 0. And u equals 1 minus 2, which means my top bound will be -1. All right, so now let's substitute everything in. All right, so I've got, I'm going to take this negative and I'm just going to move that to the outside right now, okay? Because I know it's a constant. I know it's going to get pulled out, so I'm just going to move it to the front right away. Then I have the integral from 0 to -1 of e to the u du. What do you notice about the bounds here?
They're moving to the left.
Yeah, they're like going backwards, right? -1 is at the top, but that one is smaller than 0. So we can use one of the tricks that we learned at the end of class last time. And we're gonna flip the bounds, and that means we change the sign in front, okay? So the sign in front is now gonna be positive, and I'm switching my bounds now. I have -1 down here and 0 up here. Okay, so now let's take our integral and plug in our bounds. So I get e to the u, no plus c because I have bounds, drop the line, 0, -1. and I get e to the 0 minus e to the negative 1. Now, if these were x's, you could leave them like that, but I'm going to say that we want to make sure we know that e to the 0 is the same as 1, okay? So we would actually write this as 1 minus, and then e to the negative 1, we can write it as 1 over e, okay? And so that's how we take care of the u substitution in the bounds for number 7. All right. Why don't you guys try number 8 real quick? All right, so let's try number 8. I'll put my work up on the screen in just a little bit, and then we'll move on to some other u substitution questions. All right, folks. So my work for number 8 is up on the screen. Let me know if that checks out with yours or if you have any questions. And if I don't hear anything, I'll just move on in a couple minutes. All right, sounds like we are ready to move on. So let's take a look at example number 9 over here, okay? So when I was typing this one, I was like, ooh, this just looks so much worse than the other ones, but I think in reality, it's not quite so bad, okay? So let me maybe write this a little bit clearer for you, but this is the integral from 1 to 2. And on the bottom here, I do have an x squared dx. But on the top, that's e to the power of 1 over x. Okay, so that 1 over x is supposed to be a power. So knowing that, what are our intuitions telling us should be our u?
X squared.
Ah, it's actually not the x squared.
E to the 1 over x.
It's actually not e to the 1 over x. It's actually just the 1 over x, okay? So this part right here in the power, that's going to be our u. And I know it's with a lot of other things right now, so that's a little harder to see. But let me just scroll back up real quick to like question 8. Now you all picked the u as the power, 2 to the x, all right, or 2x. And over here, we picked 1 minus x as our u. And over here, we picked our x to the 4th as the u, okay? So the purpose of showing you these previous examples is just to say, like, it's okay if things get complicated, but with e integrals and u substitution, a lot of the times that u is going to be whatever is in the power, okay? So if we follow that, we have u equals 1 over x. Maybe a better way to, maybe a better way to write that for us, because I know we have to take the derivative, is x to the negative 1. Now let's take a look at what happens. When I find my du, I get negative x to the negative 2 dx. And let me rewrite that. I get negative 1 over x squared dx. All right, so let's see what matches with my dx. Well, the dx and the dx, that matches. And this 1 over x squared is really what that's saying. X squared on the bottom is the same as 1 over x squared, okay? So the only thing I need to move for my du is that negative sign. Before we move on to the bounds, are there any questions about this u and du?
So we're just trying to make it match what's in the original function.
Yeah.
Okay.
Yeah.
Makes sense. Got it.
Okay. All right. So let's find our new bounds. For the bottom bound, we'll do 1 over 1, because that's what it is, which equals 1. And for the top bound, we'll get 1 over 2, or 1/2. Okay. So now let's substitute everything in. So I'm going to have this negative sign in the front, okay? So negative the integral from 1 to 1/2. Oh, this looks like another case where I can switch my bounds and change the sign to a positive, okay? And then e to the u du, which equals the positive integral of 1/2 to 1 of e to the u du. And that's going to give me e to the u, plug in 1, plug in 1/2. So e to the 1 minus e to the 1/2. You could certainly leave it like this. You could also write it like e minus the square root of e. And I would say either version in this case would be fine.
I guess my only issue I have here is it's just kind of weird for me to switch the original function into e, like that first part, negative integral of e u du from the original.
Oh,
But,
like how to go from here to here?
yeah, but I mean, it makes sense. It's just weird. So I guess it'll just take practice.
Okay. Well, we're going to actually do number 10, which is very similar to this, because I think it is different. Like, it's weirder when that power is negative.
Yeah.
Yeah, because
Okay.
we're used to picking the thing with the higher power as our u, which I get that a lot of people would say, oh, it's x squared, right? Because squared is the higher power. However, it's on the bottom, so it's actually a -2.
Yeah.
Yeah.
Okay.
All right. And look at how grown up you guys are. There's not even a single number in our answer, really. I mean, it's like e minus the square root of e, and you're just handling it like champs. So, well, on that note, let's try number 10, okay? So, I'm gonna do this so you can still see example 9, but example 10 is really similar, all right? So I'll give you a couple moments to try that out on your own, and then we'll go over it to see what we get.
Can you zoom in a little bit on that?
Oh, yes, of course. Is that better?
Yeah.
Okay. All right, so before we plug anything in, let's take a look at the work that you have and the work that I have on the screen here, and make sure that we all feel okay about the setup for things. So I had my u as the power for e, which in this case was 4x to the -2. I found my du, and then I had to move some things to get to like the final du that I'm going to be able to substitute. So this 1/3 to the third dx, I can replace with -1/8 du. Okay. So let's see what happens when we substitute everything in. So I'm going to start with the integral symbol. And my bottom bound is this green one, which is 4. Okay. And my top bound is going to be this blue one, which is 1. And I know that this middle term becomes e to the u. And then the orange parts, 1 over x to the third dx, I can replace with negative 1/8 du. Now that negative 1/8, again, some of us might feel super comfortable just bringing that out to the front immediately. And starting at either this step or this step is fine, okay? I think when you get to Calc 2, if that's where you're headed, that a lot of times professors will sort of start right at this second line, but it's okay for right now to say, okay, I just want to write it out so I know where it comes from. Now I notice yet again, I have this negative sign in the front and my bottom bound and top bound are sort of switched. So we're going in the opposite direction. So I'm going to go ahead and remedy that by changing the sign. So now it's a positive 1/8 and switching the bounds, small to big. And now my integral is just 1/8 e to the u. Drop the line, put the 4, put the 1. 1/8 e to the 4th minus 1/8 e to the 1. And if you wanted to, you could even write it like e to the 4th minus e over 8 and like combine them into one single fraction. I've seen those kinds of answers in other textbooks, so I just kind of wanted to show you that it could be combined into one fraction. All right, any questions on number 10 here? All right. Well, now we're going to take a look at, let's see, the last 1, 2, 3, 4, 5 questions are all going to involve the natural log ones. Okay, so let me scroll back up to the top real quick. And let's just look at our formulas again. All right, and we're going to be focusing mostly on this case. All right. I have, again, rarely seen this one or this one. It's good to know, like, you can always look it up in a table, but 9 times out of 10, when we're talking about integrals of log functions, we really mean when you integrate 1 over x, you get natural log x, all right? So that's where we're going to start, and we're going to take a look at example number 11. Okay, so I see example number 11, and I see that I have this x minus 10 in the denominator, all right? So it's different if I had like x minus 10 over 3. That would be a different question, all right? But because the x minus 10 is in the bottom, I'm thinking, well, let me try some u sub, see what we get. My du would equal 1 dx, so that's an easy swap. And when I substitute everything in, I'm going to get the integral of 3 over u du. Now, since 3 is a constant, I can bring that out to the front. And now look what I have here. 1 over u du. This is, and I'll write it up here, not the power rule. And I know we're in a section where we're not talking about really the power rule. So you're like, well, of course it's not. But on an exam, when it's like mixed up with everything else, we need to make sure we know that integral of 1 over u is not the power rule, but it's going to give us natural log of u. So that means my antiderivative is 3 natural log, and we want to put that u in absolute value. So an absolute value of u plus c. The reason we want to put it in an absolute value, those of you who know what the natural log function looks something kind of like this, okay? There's no function on the negative side. So that's why we need these absolute value bars to make sure that we're keeping everything inside the domain. And now our last step is to plug back in. Everywhere we saw the u, we're going to put in x minus 10. And that's it. Okay. Why don't you guys go ahead and try example 12 over here. Okay, I'll try and leave them both on the screen at the same time so you can still look at number 11 if you're still copying that one down, but if you're ready, you can go ahead and start on number 12. All right. So folks, what do we think about number 12? That looked to be what you all did in your process. Are there any questions about where things came from or where things went?
Yes, Professor. So, I think earlier we were talking about how we try to make or like manipulate one thing to look like something already in the function. And
Yeah.
I was just having trouble seeing how when we have 1/3 du equals dx,
Yeah.
how I'm just having trouble seeing how that looks like something in our original function.
Oh, okay. So what it looks like is this dx
Mhm.
is this dx.
Okay.
So everywhere I see a dx, I can put 1/3 du.
Okay.
So that's why, like, at the end, I put this 1/3 du because that was my dx.
Gotcha.
Yeah. So we want to try and make it look like something in the equation, but if it's got only constants, like you're dividing by 3 or multiplying by 2, that's a little less important because all the constants at the end, you can pull them out to the front anyway.
Thank you very much.
Okay. Any other clarifying questions on number 12? All right. So let's walk through number 13 together. Why don't you folks help me out here? I'll give you a moment to take a look at the question. So we have the integral of 2x cubed plus 3x over x to the fourth plus 3x squared. What would you like to select as your u?
X to the fourth plus 3x squared.
Very nice. Can you tell us, maybe like share your reasoning on why you did that? Because you're correct.
Well, we know the ln of 1 over u, the
Mhm.
integral of that, so it would just make sense to use that form.
And for those of you earlier who were like, but if it has the bigger powers, that should be our u, you'd also be correct, because this is like an x to the fourth, and that's bigger than x to the third. And this one is x squared, and that's bigger than x to the 1. Okay, so that's another way to kind of think about that. So when we find our du, we'll get 4x cubed plus 6x squared dx. Now, if I compare that to what I'm trying to substitute, I realize that everything is off by a factor of 2. So I'm going to say, let's factor out a 2 here. So we get 2x cubed plus 3x squared dx. And then I'm going to divide by that one, by the 2 to get 1/2 on the other side.
Professor?
Yes.
Why is it 4x cubed plus 6x squared? Wouldn't it just be 6x?
It would just be 6x. I was just wondering where that extra squared came from.
Okay, it's just like, wait.
And it came from, it's Thursday and I haven't finished my coffee. Okay. So now we're good, right? Now everything matches?
Yes, it
Yeah.
does.
Okay, cool. All right. So everywhere I see this 2x cubed plus 3x dx, so this top part, when I rewrite my substitution, all of that just becomes 1/2 du. All right. And let's substitute. So I've got the integral of 1 over u times the thing in the orange is going to become 1/2 du. Any constants, I'm going to pull those out to the front. And then I'm going to take that integral, which is the natural log of u plus c. And then I get 1/2 natural log of x to the fourth plus 3x squared plus c. Okay. So this would be one version of my final answer. But you'll sometimes find that professors, especially in Calc 2 and Calc 3, can be pretty particular about notation. So a lot of times they really want you to have that absolute value bar. But then every once in a while, they'll be like, or you could have an answer like, not that. This, or you look it up on Chegg and it has parentheses and not absolute value. And you're like, what? Because I thought you had to have the absolute value. So in this case, you could be correct with either option. And let's talk about why. Let's look at the thing inside the parentheses, so, or absolute value. So x to the fourth plus 3x squared. That's the thing that we're saying always has to be positive. That's why we put the absolute value bars around. But if I take any number and I raise it to the fourth power, will that number be positive or will it be negative?
Positive.
It's going to be positive, exactly. Because if I do like -1 to the fourth power, it'll be like -1 times -1 times -1 times -1. So ultimately, it's going to be positive. All right, well, what about x squared? Positive or negative?
Positive.
Positive. All right, what about 3? Well, maybe that's too easy of a question, but 3 is always going to be positive, right? It's plus 3. So what happens when you take a positive number plus another positive number?
Then
This
another
is
positive.
always going to be positive. Okay, so in cases where the thing inside is always going to be positive, sometimes folks put the parentheses. They don't put the absolute value because they're like, look, I already know it's going to be positive, so I don't need the absolute value. Okay, so that's why once in a while you'll see 2 different versions of an answer. But if the number inside is not guaranteed to be positive, then you need the absolute value bars. All right, so our last 2 examples before we go on a break will be definite integral questions that involve natural log, okay? So let's take a look at example number 14. So if I were to look at this, I would say that I want my u to be the thing on the bottom. All right, so in this case, I'm going to pick 1 plus cosine x. And that would leave me with my du to be negative sine x dx. And I'm going to divide that negative to the other side because I see that I have a sine x dx, not a negative sine x dx. And then because it's a definite integral, I'm going to find my bounds. So 1 plus cosine 0 is 1 plus 1, which equals 2. I was just thinking about if I wanted to write that on a separate line, not like I didn't know that 1 plus 1 was 2. Okay, so for the top bound, I've got 1 plus cosine of pi over 2, and that's going to be 1 plus 0, which is going to give us 1. All right, so let's substitute everything in. I'm going to get the integral from 2, because that's the green one, to 1, because that's the blue one, of 1 over u times a negative du. So again, that sine x dx got replaced and became negative du. Now I can go ahead and pull that negative out to the front. And then I can also do that, switch my bounds and make it positive trick. So 1 to 2, 1 over u du. And that will give me natural log of u. I'm going to go ahead and put it in absolute value bars, and then 2 and 1. So when I plug in my numbers, I'm going to get natural log 2 minus natural log 1. And I don't need the bars anymore because 2 is a positive number, 1 is a positive number. Now we do want to make sure we know though that natural log 1 is 0. So our only answer is natural log 2. Okay. Now I think you'll see questions kind of like this at the beginning of Calc 2. And what'll happen is sometimes like a lot of these first couple steps, like your professor might skip over them, or like Chegg might skip over them, or Slater might skip over them. So it's important that like if someone shows you this and then they jump right to here, it's okay to write out a couple steps and say, okay, let me see if I can figure out how they got there, instead of just panicking and being like, I don't know how they got there. Okay, so folks are going to start to skip steps at this point in your academic career, and it's kind of up to you to fill in those gaps, like how did you get from here to here, okay? All right. Any questions on example 14? Okay, so we're going to do, oh, I didn't change the number. This should be example 15. Okay, so funny story about this question. So I used to teach high school, and I taught Calc AB in high school. And in the AB curriculum, you don't have to do the integral of tangent. So because I was only teaching AB, I was like, well, I guess I just don't need to remember this. But then I took like a teacher test, and it was like a 3-hour-long test, and it had like all these questions on it. And one of the questions was this question. And I was like, what? I was like, how is this on the test? I didn't study for it. But it turns out that even if you don't memorize this rule, okay, because it's not one of the sort of nice common integrals, this is actually a very sneaky way and a very clever way of using U substitution and trig, okay? So it begins by saying, you know that tangent is the quotient of sine x over cosine x. This is how this starts, okay? So I know that tangent x is the same as sine x over cosine x. So let me write it in that way and see if that helps me figure out my integral. And turns out it does, because now I can see that I could try U substitution. All right, so I'm going to let U equals cosine x. That makes my du negative sine x dx. But I notice there's no negative sign, so I'm going to divide that negative to the other side. And then I'm going to plug in my bounds. And I'm going to plug in my other bound. And now I'm going to substitute everything in, okay? So the reason why I wanted to show you this question is because I think it sort of shows a need for how we can use some integration rules to help us find other integration rules. Okay, so I've got the integral from the green number to the light blue number of 1 over u times negative du. And I'm going to move that negative to the outside. And I'm going to go ahead and switch my bounds. Okay. Now this switch your bounds trick, it's helpful, but you don't have to use it. Like, people do the problem without it just fine. I think I just find it useful in cases where there's a negative in front, because then I don't forget about a negative sign. All right. So I take my integral, I get negative or natural log of absolute value of u. I'm plugging in 1, and I'm plugging in root 2 over 2. And I'm going to get natural log 1 minus natural log of root 2 over 2, which is going to give me negative natural log root 2 over 2. Okay. All right. Any questions on example 15? All right. well, let's do this. It is 10:45 right now. Let's take a quick break. Let's be back in 7 minutes. So 10:52, be back here. Diana, if you wouldn't mind pausing the video. And then when we come back, we're going to start with 5.7. So we're going to start the second half with 5.7. I already see a few of you on that document. So again, if you want to access the document through Canvas, if you click on the 5.7 tab, then all the blank notes should be there. And again, you're welcome to print that out or import it into your tablet or whatever makes sense for you. And I'm going to go ahead and start sharing my screen. All right. So let's take a look at the last section in chapter 5. So this section is 5.7. And so this is the last sort of set of rules that we're going to learn integration in Calc 1. In Calc 2, you learn a lot more rules of integration. So you learn way, way more rules than what we're gonna do here. But in order to do the next ones well, it's really important you have a good understanding of what we're doing now, okay? So here are the 3 rules that we are going to focus on here. So we're looking at ones where at the end, we get some sort of inverse trig function. And I tried to pick the ones that were like the most common, but I will tell you from my experience teaching 151 that this one comes up a lot, the inverse sine one. Okay, so key things to look for in the inverse sine, it has the square root. And on the bottom, it has a squared minus u squared. And just to clarify, a is going to be a constant or a number. So that means a squared is also going to be a number. And okay. And let me just get rid of that part. All right, so the square root here, you've got your a, and then your u is going to be some function with x, all right? That is going to give you the inverse sine of u over the absolute value of a. Another super common one is the inverse tan one. And so what's different about this one is there's no square root, and it's a number squared plus some function of x squared. And when you find that integral, you will get this. 1 over a inverse tan of u over a plus c. Now, your textbook talks about this third one here, the secant one, but truth be told, I've seen this one pretty rarely in Calc 2. Okay, so this is definitely the least common for Calc 2, all right? So for that reason, we're going to spend most of our time today, focusing on recognizing these first 2 and not so much on the last one, okay? I just wanted you to know that there are other inverse trig functions, but the arcsine and the arctangent are like the most common ones that come up. Okay. So let's go ahead and jump right in. So we're going to start with example 1 here, which is a definite integral case, all right? And so we'll get a chance to practice recognizing which one we're going to use and how that works. Okay, so in this case, I have my square root on the bottom. All right, so automatically I'm looking at this and thinking I need arcsine of u over the absolute value of a in my answer. Okay, so I see the square root of 1 minus x squared, and I'm thinking that looks a lot like the square root of a squared minus u squared. Okay, so let's go ahead and figure out what our a is and what our u is. So my a squared is 1, so my a is 1. And my u squared is x squared, so my u is x. So everywhere that I see an a, I'm going to be able to put 1. And everywhere I see the u, I'm going to be able to put x. And let's go ahead and write out what that would give me. So the integral, nope, already did that part. We're going to do arc sine of x over absolute value of 1. No plus c because it's definite, but I'm going to drop the line and put the 1/2 and the 0. That's going to give me arc sine of x. I'm going to plug in 1/2, and I'm going to plug in 0. Arc sine of 1/2 minus arc sine of 0. So this is a good chance to review what an arc sine means, but this part means find an angle with a y value of 1/2, okay? However, that angle needs to be between negative pi over 2 and pi over 2, okay? So if we think about our unit circle, that means the angle that we get that has a y value of 1/2, that is on the right half of the unit circle, will be pi over 6, okay? And then for this part right here, it says something similar. It says find an angle with a y value of 0. And same thing, that angle needs to be between pi over 2 and negative pi over 2. So when we look back at our unit circle, the angle that has a y value of 0 is actually 0. And so our final answer here is going to be pi over 6. All right. So a good example of how you just kind of plug in the numbers, you have to be able to recognize the a and you have to be able to recognize the u. Okay, so it's not a bad idea to take that extra step to sort of write that out here, because when you take the time to do that, it becomes way easier, I think, to plug in to your formula. All right. So let's take a look at examples number 2 and see how that's going to be similar or different. So for example number 2, do we think our answer is going to end up being arcsine or arctan?
Would it be arc sine?
What's up?
Would it be arc sine?
Yeah, this one is going to be, yeah, this is going to be arcsine. And so I know the arcsine is going to be u over the absolute value of a. So it's going to be really important that I identify my u and I identify my a. All right. So in this case, a squared equals 1. That makes a equal to 1. I just take the square root of both sides. Now I have to find my u. So my u squared is 16x squared. So like I have to take the whole thing. I can't just take part of it. What does that make u in this case?
4x.
Perfect. 4x. So you have to take the square root of the x and you have to take the square root of that number, okay? And so when we plug this into our formula, we will get arc sine of 4x over 1. And nobody's going to write that 1 on the bottom, so we can just say arc sine of 4x plus c. Okay? So how about you guys try number 3 here and number 4, okay? So hopefully you can see both questions on the screen right now. Take a look at 3 and 4. See if you can identify your a squared and your u squared, and then from there find your a and your u, and then plug it into your formula. All right. So here is example 3, okay? So in this case, we have a different number for a squared and u squared. So we have to take the square root of both of those. So we'll get a is equal to 2 and u equals 3x, not 9x, but 3x. And then when we plug them into our formula, we should get arc sine of 3x over 2 plus c. Okay. Now let's check over example 4 here. My a squared is going to be 9. That makes my a equal to 3. And my u squared is just x squared. And then that makes my u equal to x. And so based off of the square root on the bottom and an a squared minus u squared, I know it's going to be arc sine. And it's arc sine of u over a, and then plus c. All right. So 3 and 4 are both on the screen right now. Are there any questions about either 3 or 4? Okay. If there are no questions, then I'm going to ask you to take a look at number 5. Okay, so number 5, we're going back to the definite integrals. All right, so I want to give you a chance to work over this one. If you need to pull up a unit circle on your computer, that's fine. All right, but I would make sure that that unit circle gets onto your cheat sheet for exam number 3. Okay, so if you need to go ahead and pull up a unit circle right now to help you find the values that you need, that's fine. But let's go ahead and do that. And I'll give you a few moments to work on this problem before I start working through it on the iPad. All right, folks. So let's take a look at example 5. I'll give you a couple of moments to look at the screen. If you have any questions, let me know.
I have a question about the initial steps when you go from like a squared equals 1 to a equals 1.
Yeah.
Why are we only accepting positive values of the square root?
So we're taking the positive values because let me scroll back up to the top for a moment. If you look at the formula on the bottom here, do you see how it says absolute value of a?
Okay.
Okay. So if you're right in that technically the square root of 1 is 1 or -1. But I'm just going to take the positive value because I know I need to take the absolute value.
Okay, that makes sense. Thank you.
Cool. All right. Other questions on number 5? All right. Well, we're going to do a few examples using that result in arctan, and then we'll call it a day. Okay. So let's take a look at example 6. And I'm going to leave example 5 on the screen real quick, just so we can kind of compare and contrast, okay? So when I look at number 6, I'm like, oh, I've got like a something squared plus something squared on the bottom. So automatically I'm thinking it's going to be some sort of inverse trig. There's no square root, and it's a plus sign in between the two things. So together that tells me that my answer will be that inverse tangent, okay? And since this is the first time that we're using that, let's actually just write down the whole formula, which is going to be 1 over A arctan of U over A, and then plus C. Okay. So let's go ahead and identify our A squared is 1, A is 1. Our U squared is 4x squared. That's going to make U equal to 2x. And so let's plug everything into the formula. I'll get 1 over 1 arctan of 2x over 1 plus C. Or I can just say arctan of 2x plus C. All right, so different formula, but straightforward in the sense that if you can identify your A and your U and you just plug them in, then you'll be able to get to your answer. So it's more about recognizing it than necessarily it means that it's like harder, okay?
I have a question.
Sure.
So how can you tell by if you need to use a U sub or use this formula?
Ah, that's a really good question. So let me pretend like I didn't know I was supposed to use the inverse trick, okay? And so let's copy this problem down here for a second. So let's say I had the integral of 1 over 1 plus 4x squared. And I was like, well, we've been doing a lot of U subs, so let me try that. So I would set my U equal to 1 plus 4x squared. Yeah? And then I would look for my du, and I would get 0 plus 8x dx. Now, when I look at my equation, I see a dx in the equation, but here's what I don't see. I don't see an x. Like, there's no x on the top here. So I can't use U sub.
Okay, I think I got it.
Okay. However, if I write the question like this, the integral of 8x over 25 plus 4x squared. Okay. So same things I see on the, whoa, I'm writing a different problem. Sorry. Okay. 8x over 1 plus 4x squared. This one, I would use U sub. And the reason why is because I have that matching part for the du.
So on the left side, are you not allowed to like divide it by 8x?
Ah, okay. So I think it was Gerardo who asked earlier, like, how do you know what you need to move? So you can move constants. Like I could move the 8 and that would be fine. But I can't have a 1 over x hanging out in front of my function.
Okay.
So like if I divided, I'd get du over 8x equals dx. And then if I tried to plug that into the question, I would get the integral of 1 over u times 1 over 8x dx, or sorry, du. So the problem here is I have some u's and I have some x's.
Okay.
Okay, so that's why, like, if you end up with a variable in there that you can't match, then that's definitely a case when you're not using U sub.
Okay, thank you.
Okay. I really like her question, by the way. So folks, that was a super, super good question, because I think that is a question I heard a lot from my Calc 2 students. They're like, well, wait, but how do you know? So you do have to check if you can find part of the derivative somewhere else in the function, go with the U sub. But if you have an extra variable hanging out, then you can't do the U sub, okay? So let's actually skip number 7. I think it's similar enough to the other ones. Let's maybe try example 8, and then we'll do 10 and 11, and I think we can call it a day, okay? So with number 8, let's again maybe pretend like I didn't know, right? So if I tried U sub, which is a good one to try first, I get stuck because there's no x in my integral, okay? So as soon as I try that, I'm like, nope, no U sub. So then I'm like, well, I see something squared plus something squared on the bottom, so maybe it's my arctan. And we're able to identify our A, and we're able to identify our U. So that's going to give us 1 over A, the arctan of U over A plus C. Okay. Any questions about number 8? All right. So let's do this. I'm going to have you guys try number 11. Okay. Try number 11. Think about the setup. It's got bounds, so that means that we're not going to have a plus C at the end, but we are going to have a number at the end of our answer, okay? And then we'll go back and finish off with number 10 together at the end.
Would these formulas work even if you could do U sub?
No. So it's like an either or. Like either it's going to be U sub or you're going to be looking at the arctan.
Okay, thank you.
Mm-hmm. All right, folks. So I really appreciate these questions about how do you know when to use what. And I think, sort of thinking forward, and I know that the school is sort of like in flux. We don't know if we're going to be in person or online, but I think that's a really valid question to ask any professor, especially in math, like, well, how do I know that I'm using this technique? And how do I know that I'm not using this other technique? Okay, those are really good questions to ask. And I think they also help you decide before you get to a test, well, like, how am I going to know when to use what? Okay. So if we plug everything into our formula, we should get this line right here. So I've got a 1/2 arctan of x over 2. I'm going to plug in the 2, and then I'm going to plug in the 0, and I'm going to subtract them. And so when I get to this final line, okay, so arctan of 1 is asking which angle has a tangent of 1. And another way to think about that is which angle has the same sine and cosine. And so that angle is pi over 4, okay? And then the next part is asking where is the tangent equal to 0? And this is actually always going to be the same as when arcsine equals 0, okay? So that's going to give us 0 radians. And when we clean that up, we'll get pi over 8 as our answer. That's the other thing about moving on to like future classes is you're pretty much not going to be using degrees. Everything, a lot of the things will be in radians. So make sure that that's something you feel really comfortable about before you move on to Calc 2. Okay, so like the radians definitely don't go away, and rarely do you use degrees. All right, so are there any questions on number 11?
Yes, Professor. Can you hear me?
Yes.
So after you have there a equals 2 and u equals x, right after that, the line below it, that 1/2, where did that come from?
Oh, okay.
Yeah.
Let me write the formula. So this is going to lead us to the arctan formula, which is 1 over a arctan of u over a. So like I know the integral of that is going to be this.
Okay.
Okay.
Yeah.
And the reason why I know that is I see 2 squared plus x squared on the bottom, and that's making me think arctan.
Okay.
Okay.
Thank you.
Of course. All right. So with that, let's go back and do number 10. Okay, I think the tangents are always a little trickier for folks. Like sine and cosine we can pretty much handle, but tangents always seem a little harder. So let's go ahead and finish off with a little bit of a challenge together. Okay, so I'm going to scroll back up to number 10. And let's take a look at what we have. So identifying factors, I see a squared plus an x squared. They're on the bottom. I don't see any derivative of x squared in the equation, so I'm ruling out in my head u sub. So if I know I'm not using u sub, that means that I'm using arctan, and that my answer should be 1 over a arctan of u over a. All right, so I know that's where I'm going. In order to get to my answer, I have to identify my a and my u. Whoa. So my a in this case is 1, my u is x. So that means that this integral is going to be 1 over 1 arctan of x over 1. And I'm going to plug in root 3, and I'm going to plug in root 3 over 3. Okay, so this is going to give me arctan of root 3 minus arctan of root 3 over 3. Top bound minus bottom bound. And a lot of things sort of look like they went away because 1 over 1 just goes to 1. And then x over 1 just goes to x. All right. So now we got to find some values on the unit circle. Okay. So arctan of root 3 means that I had to divide sine divided by cosine got me root 3. Okay, so let's take a look at that off to the side. So if tangent x equals root 3, then that means sine x over cosine x equals root 3. So let's kind of go backwards. How did I end up with root 3? Well, I know that all of the values are like something over 2. So I'm going to kind of fill that in already because I know the unit circle values are like something over 2, something over 2. And I want to end up with a root 3. So my options are, it could be like the root 3 over 2 over 1 over 2. Or what if I do 1/2 divided by 3, root 3 over 2, okay? So those are sort of my two options. So what I'm gonna do is I'm gonna write them as like the fraction, the top fraction times the reciprocal of the bottom fraction. And I'll do the same thing here. I have the top fraction times the reciprocal of the bottom fraction, okay? So which one of these, option A or option B, simplifies to give us root 3?
Option B.
Option B, yeah, because this 2 and that 2 will cancel. So that means that this one, let's say, is not correct for this, okay? But we can probably use it for the second part. So now I want you to find an angle on your unit circle that has a y value of root 3 over 2 and an x value of 1/2. And when you find that angle, you should get that that is going to be pi over 3, okay? So another thing, or another way to say that is that arctan of root 3 equals pi over 3. So that means that this first part here, I'm going to replace with pi over 3. Now, if you're thinking that like you're going to go beyond Calc 2, this is kind of a nice one to add to your memory bank, okay? There are so many things to add to there, but that one might save you a little bit of time from doing this every single time, okay? If Calc 2 is kind of going to be the end of the road for you, then, you know, I'll leave it up to you about what you want to memorize and what you don't. But if you're going to move beyond that, I think it does become like useful to kind of know. Okay, so let's take a look at this second part. So now I need to find a place where I do y divided by x, and I get root 3 over 3. So let's take a look at the thing I circled in the red. Okay, I said that wasn't right because it didn't give us root 3, but let's see what happens when I do simplify. These 2's are going to cancel, so I'll end up with 1 over root 3. Okay, but once upon a time, you probably had an instructor who was like, no radicals on the bottom. And so you were like, okay, well, if I want to get rid of that, then I can rationalize it. And that would give me root 3 over 3. Okay, so 1 over root 3 is the same as root 3 over 3. Those are not different quantities. They are the same. And the angle where I have a y value of 1/2 and an x value of root 3 over 2, that angle is pi over 6, okay? So let me write that down here. Another way to remember that is the arctan of root 3 over 3 is pi over 6. And so I can put pi over 6 here. And then I'm going to make a common denominator. So this will be 2 pi over 6 minus 1 pi over 6, which will give me 1 pi over 6. Okay. So I know that one is definitely a bit more work than example 11, okay? But I just want us to remember that like all the stuff we ever learned about tangent definitely comes back in these problems. And sure, they're harder than the ones that don't use tangent, but it's not totally out of the realm. It's not like way hard that you couldn't actually do it, okay? It's definitely doable, but it's a choice about like, do you want to go through this process every time? Do you want to memorize it? What do you want to do with that information, okay? All right, so are there any questions before we finish up here today?
I have a question, but it goes back to what we were doing in 5.6.
Okay, sure. Let me go back to that document. All right, here we go. Which question?
Number 13.
Cool. This one?
Yeah.
Okay, what's your question, lady?
So when you were choosing u, you said that the bottom exponents were bigger because it was 4 and the top one was 3. But wouldn't it be -4 because it's under?
But you're using the whole thing as your u. So it's like if this is your u, that means the powers are +4 and +2.
Oh, okay.
Does that make sense?
Yeah, that makes sense.
Okay. Yeah.
Thank you.
Mm-hmm. Great question. All right. Any other questions right now, folks?
Actually, I have a question about a problem on WebAssign.
A question on WebAssign? Sure.
Yeah.
Okay. Let me just come back into the Zoom room real quick.
A quick question for the inverse.
Okay. So folks, if you don't have any other questions on the content, you're welcome to take off. If you want to hang around for a little bit and just like wait for some other questions to come up and see if they apply to you, you're totally welcome to do that as well, okay? So I just want to let you know that if you want to take off right now, you're totally welcome to. And while you are figuring that out, I'm going to go ahead and pull up WebAssign so I can answer that question, okay?
Thank you. See you on Tuesday.
Okay, bye.
Ask you a question for the inverse trig.
Mm-hmm.
So do you not change the bounds when you do like when it's bound? You know, like
Yeah, you don't change the bounds because we're not doing a U substitution.
okay, so you only change them when you do U sub.
Yeah.
Yeah, got it. Thank you.
Cool. Great question. All right, 150 unit 3 homework. All right, what question did you have on web?
It was number 19.
Number 19. Okay, let me go ahead and pull that one up. Okay, what was your question about number 19?
It was part C where the question was repeat part A using midpoints. So you're trying to find what M3 and M6 equal to.
Oh, okay, like how do you do the midpoint part?
Yeah.
Okay, cool. Let me go back and share my screen and then we will figure that out.
Yeah. Perfect. Okay. But ahead of time, understand.
All right, so I'm going to stick this at the end of the 5.7 one, okay? So web assign number 19. Okay. So part C, we're looking at the MRAM. So can you tell me what your function is? What is your f of x? Gabby?
Oh, sorry, it was on mute.
That's okay.
I think f of x was 1 plus 2x squared.
Okay, and are you going from -1 to 2?
Yes.
Okay, cool. So for the MRAM, okay, let's start with the MRAM with the 3 rectangles. So for 3 rectangles, you're going to do B minus A, and you're going to divide it by 3.
Okay.
So that'll tell you the sort of width of each rectangle. Then you have to figure out what the middle point is for each rectangle. So if you look at the diagram for part C, all right, the first rectangles is between -1 and 0. So like I have -1, 0, 1, and 2. So where is halfway between -1 and 0?
It's at 1.
What's the number halfway between -1 and 0?
Oh, 0.5.
0.5. Okay, so I'm going to say I want to find f of -0.5. Because this will give me the height of the rectangle that is halfway between -1 and 0.
Okay.
Okay? Now, the number halfway between 0 and 1 is 0.5. So I'm going to try and find f of 0.5. And then the number that's halfway between 1 and 2 is 1.5. Okay? And so when you clean this up a little bit, you'll get 3 over 3. F of -0.5, I can just say is 1 plus 2 times -0.5 squared. So I'm literally just plugging it into the function. Plus 1 plus 2 times 0.5 squared plus 1 plus 2 times 1.5 squared. Okay, so like this f of -5, I just plug -0.5 into the function. F of 0.5, I just plug 0.5 into the function, and f of 1.5, I just plug 1.5 into the function.
Okay.
Okay? So let's do the same setup, but for what happens if you had 6 rectangles, okay? So 6 rectangles means 2 minus -1, because I'm still using my same B and A. And this time, though, I'm dividing it by 6. And this will give me the width of each rectangle. Now, to help me figure out these parts, I'm going to draw a similar diagram, okay? So if I go from -1 to 0 to 1 to 2, but I want 6 rectangles, that means I have like -0.5, I have 0.5, I have 1.5. So now I've divided that space into 6 rectangles. So let's take it rectangle by rectangle. What's halfway between -1 and -0.5?
-0.75.
Perfect. And so you're going to write f of -0.75 as the height of your first rectangle. Plus, what's halfway between -0.5 and 0?
-0.25.
Good. All right, and then you keep going with that pattern. And you should have 6 of them all together. Yeah? Okay, and then you're going to find each of these the same way you found them from before. You're going to take -0.75 and you're going to plug it into the function. and then you're going to find negative 2.5 and you're negative 0.25, and you're going to plug that into the function. And each time you do that, that'll give you the height of another rectangle, and you should do that a total of 6 times.
Okay. Okay, that makes a lot more sense.
Okay, good. I'm glad. All right.
Thank
So when
you.
I post the notes for 5.7, this will be on the very last page, and so you can go back and look at that. Okay.
Okay, perfect. Thank you so
All
much.
right. Cool. All right. Anybody else have any questions out there?
Okay, bye. Thank you.
Okay.
See you later.
Bye.
Bye, thank you.
Bye. All right. Diana, I think we can stop the recording now.
Okay.
Okay. Thank